Hello, everyone. I'm Maria Thomas, and presenting with me is my partner, Kayla Johnson. For our CS620 final project, we analyzed NYPD Stop-and-Frisk data to examine fairness and accountability in policing. We focus on the three benchmark years 2012, 2017, and 2022 because each represents a distinct point in the broader stop-and-frisk landscape. 2012 represents the peak controversy period, and 2022 gives us a recent post reform snapshot. But 2017 is the first year with complete, stable, post reform data and a consistent schema, making it the best foundation for accurate modeling. So 2017 anchors our inferential analysis, while 2012 and 2022 provide broader context. Today we'll walk through our cleaning process, our fairness focused model, and what we found. A key motivation for our analysis is a 2015 statement from Mayor Michael Bloomberg claiming that police focus on minority neighborhoods because that's where all the crime is. Statements like this influence policy and public perception, but they can be tested with data. Our goal wasn't to take a political stance, but to use data science. Using the clean 2017 dataset, we applied statistical tests and fairness metrics to examine whether meaningful disparities exist in policing outcomes. The NYPD's 2017 dataset originally contained nearly 12,000 rows and 86 variables. A major part of this project involved correcting mislabeled race categories, fixing mixed type sex values, removing null placeholders, standardizing labels across the dataset, and consolidating the final modeling ready data frame. After aligning schema across years and standardizing inconsistent entries, like cases where male ended up in the race field, we recorded all binary flags into 0 and 1, corrected categories, and handled missing values. We then selected race, sex, frisk flag, and search flag as predictors, applied one hot encoding, and used an 80-20 stratified split. These steps were essential to ensure that all later analysis, logistic regression, chi-squared, and Cramer's V were based on clean, reliable data. To clearly show arrest outcomes, we separated them from frisk outcomes. Here, the arrest rate by race shows noticeable differences, with white and white Hispanic individuals having slightly higher arrest proportions. But when we look at arrest rates by sex, males and females have almost identical arrest proportions. This distinction is important because it shows that disparities in arrests are relatively small. When we look at rates, the patterns change. By sex, males are frisked at much higher rates than females. By race, we also see differences, although not as large as the sex difference. The key point is disparities are stronger at the frisk stage than at the arrest stage. With the clean data, we trained a baseline logistic regression model to estimate the probability that a stop results in an arrest. Here's what these evaluation metrics mean. The heat map shows correct predictions in dark blue and mistakes in light blue. It gives a quick visual summary of where the model performs strongly. Accuracy, which is about 84%, tells us the overall percentage of correct predictions. In most applied machine learning contexts, anything above 75 to 80% is considered strong for a baseline model. Precision tells us how often the model is correct when it predicts an arrest. In this case, it gets 674 right out of 961 arrest predictions, giving us a precision of about zero point 0.7. Recall tells us how many actual arrests the model successfully identifies. Here it captures 674 out of 848 real arrests, giving us a recall of about zero point 0.8. The F1 score balances precision and recall. Using our values of 0.701 and 0.795, we get an F1 of about 0.745, meaning the model performs consistently across both false alarms and missed cases. AUC is computed from the ROC curve, which plots the true positive rate against the false positive rate at every possible probability threshold. The value of 0.858 means the model can correctly distinguish between arrested and non arrested cases about 86% of the time. Overall, these metrics show that even a simple, interpretable model performs reliably on this dataset. Our main goal is fairness. In the next slide, we're going to show whether these predictions behave consistently across race and sex.
Here we check fairness in model predictions. On the left, you see predicted arrest probabilities by race. The pattern we observe is that white and white Hispanic suspects tend to have slightly higher predicted arrest probabilities, while Asian Pacific Islander and American Indian groups have lower predictions. This largely mirrors the imbalance already present in the dataset rather than bias created by the model. On the right, we have predicted arrest probabilities by sex. Female suspects show slightly higher predicted arrest probabilities and noticeably more variance. Male suspects show a more compact range. Again, this may reflect sample size differences rather than model behavior. Overall, nothing here suggests major bias from the model, but as responsible analysts, we follow this step with a formal chi-square test in step 13 to see whether these differences rise to the level of statistical significance. Because both race and sex are categorical, we use a chi-square test of independence to evaluate whether predicted arrest outcomes differ across groups. Our null hypothesis says predicted arrest outcomes are independent of race or sex. The alternative hypothesis says that there is an association. For race, the p-value is 0.013, below 0.05, so we reject the null hypothesis. This means differences across race are statistically significant rather than random. For sex, the p-value is 0.618, much higher than 0.05, so we fail to reject the null hypothesis. There is no statistical relationship between sex and predicted arrest outcomes. Chi-square test tells us whether a relationship exists. To understand the strength of that relationship, we now move to Cramer's V. Cramer's V measures effect size on a scale from 0 to 1. Here you can see both effect sizes plotted on a standard strength of association scale. Both values are clustered near 0. Race shows a very small effect, and sex is essentially 0. For race, Cramer's V is 0.057, which is considered a very small effect. This means that although the chi-square test flags significance, the actual impact of race on predicted arrest outcomes is minimal. For sex, Cramer's V is 0.013, essentially negligible. This confirms that predicted arrest probabilities for males and females are nearly identical. Together, these results show that the model exhibits low demographic influence and behaves fairly within the limitations of the dataset. Before we close, let's return to the claim that inspired this project. Mayor Bloomberg's 2015 statement, where he suggested that crime follows a predictable racial profile, so predictable that you could Xerox a description and hand it out. Our analysis set out to evaluate whether the data actually supports that kind of certainty. Here's what we found. Race did show statistical differences in predicted arrest probabilities, meaning the groups don't all look identical. But when we measured the practical significance using Cramer's V, those differences turned out to be very small. In other words, yes, the model detects some variation by race, but nowhere near the level implied by a copy and paste profile. Sex showed no meaningful differences at all, statistically or practically. So, taken together, our findings suggest that demographic variables, especially race, do not strongly drive predicted arrest outcomes in this dataset. And that means the justification for the broad, aggressive stop and frisk strategies is not strongly supported by the underlying predictive patterns in 2017 NYPD data. Ultimately, this analysis reinforces that crime patterns are complex, and reducing them to a single demographic explanation oversimplifies the reality. Our next steps would be to extend this model to additional years, incorporate contextual predictors, and test more advanced models to ensure fairness and accuracy. Thank you for watching our presentation. We appreciate your time.